Hello there, we've got our fourth section in this unit. This one's all about power. See how quickly we can move to this one. I think this will be the shortest. So power, we want to understand what that is. That's the first purpose. We want to solve some problems. Not surprising. So power is the rate of doing work, meaning we want to see how much time it takes to do work. The units for this are either joules per second or watts. And here's your equations. Like I said, work over time, or because work is equal to change in energy, it's also change in energy over time. So these are your two equations for power. It's just taking what we've done before, dividing it by time. So it's not overly complicated. So let's suppose we've got a tired old wrinkle slug and it's making a 42-meter vertical climb and it takes 67 minutes and 3 seconds. It's a big climb. What is its average power output during that climb? So here's our equation. Power is change in energy over time. We just jumped straight to that one. Since it's moving upwards, I said it's potential energy. It doesn't say anything about speed or change in speed, so we're not going to deal with change in kinetic energy. Change in potential energy is mg delta h, since m and g are not changing. And in this case, we need to convert the time into seconds. So 67 minutes times 60 converts into seconds plus 3 because there's that extra 3 seconds. Plug these numbers in, you get a power of 0.113 watts. Again, it could be joules per second, it doesn't matter. Now we have an inhibitor slug. It's bored from sitting at his desk all day and needs to let out some energy. And maybe you need to, I need to. I always get antsy when I make these videos. It's hard to teach while sitting. So it accelerates from rest to 2.5 meters per second in 9 seconds. Calculate the power output. Now we're going to ignore friction in this case because that'll just make things a little bit more complicated. Power in this case is change in kinetic energy. Since we have a change in speed, you're moving horizontal, not vertical. So horizontal movement, we've got kinetic energy that's changing. Since we started from rest, my change in kinetic energy is just the final kinetic. We're not dealing with the initial at all because the initial is 0. Plug in numbers, we get 0.417 watts. So there's another useful formula that we can use with power. If we combine the equation of power equals work over time, work is also force times distance. I didn't show you that one, but work is force times distance. Distance over time, that should look familiar to you. This is just your speed equation or velocity equation, depending on if it's displacement or time. So we can get the equation that power is force times speed. Now this only works if you have constant velocity. Since d over t is a constant velocity equation, if we're accelerating, this won't work. Question, such as this. If you've got Spencer uses 50 newtons to push Doomslug up a ramp into her spaceship, if they travel at a constant velocity, so constant velocity immediately tells you that you're dealing with a case where you can do F times V, we want to know Spencer's power output. FV, you have those, plug it in. So this is not too hard as long as you're recognizing it's a constant speed. Don't plug it in when it's not possible. There you go. I told you this one's short. That's power. 2 sections left, and then we will be done with energy. All right, so we're returning back to Superman for another video here. This one, a different part. A little bit of context. Again, this is the end of the movies, so if you haven't seen Superman from 1978, just be fair warned. I think you've got plenty of time to have seen it. At this point, it's your fault, not mine. Yeah, so this one, it's at the end. His love interest, Lois Lane, dies, and so he's going to do something crazy, and he's going to fly around the world. And he's going to fly so fast around the world that he's going to turn the world backwards and turn back time. So let's watch this. Okay, so there's the clip with him turning back time. Obviously, the turning back time part is not true, but it's this whole thing of, okay, so let's just assume for a sec that Superman can fly around the Earth, and he is going to stop. As you can see here, he is going to slow the Earth down by going so fast around the Earth that he stops it from spinning, and then it starts spinning in the opposite direction. Okay, so let's assume he could do that. The problem is this. In order for him to fly back or around Earth so fast that it stops the Earth from spinning and spins it the other direction, he must be moving pretty fast. He's not touching the Earth. Really, it's him going around it and just the, I don't know, his friction, his air resistance, I don't know what he's applying to the Earth, but whatever it is, it's if it's enough to spin the Earth in the other direction, that's a problem, because then he's going to create quite a bit of chaos. With that wind, it's going to destroy a lot of things on Earth if he's just kind of blowing it or flying fast enough that it blows around the Earth to continue to get it to spin in the opposite direction. So I know everyone complains about the new Supermans. They cause so much destruction by destroying all the buildings. Well, this one would have destroyed a whole lot of things just based on the wind that he generates as he spins around the Earth to be able to spin in the opposite direction. That is what is wrong with this one.